Applications of the definite integral. Our objectives are to interpret the integral as a rate of change and interpret the integral as an accumulation function. If capital F is any antiderivative of f on the closed interval a to b, then capital F prime equals f. So the definite integral from a to b of f of x dx is the same as the definite integral from a to b of capital F prime of x dx, which equals capital F of b minus capital F of a. This is the fundamental theorem of calculus, but notice how we have the definite integral of capital F prime of x, a derivative. A derivative represents a rate of change. So when we are taking the integral of a rate, that rate goes away. So let's talk about some things that you want to make sure you're aware of when we're doing this fundamental theorem of calculus. The integral from a to b of the rate of change of capital F equals the change in f from a to b. When we evaluate f at a value b and evaluate f at a value a and subtract them, that's the change in that function f from a to b. That's the change in f from a to b. Our definite integral, of course, also means the area, or rather the net area when we have some of our function below the x-axis, and the accumulation, or the total change. Our accumulation function is that capital F of x equals the integral from a to x of f of t dt. Let's look at some examples. 1. Find the area under the graph of f of x equals e to the x from -1 to 1. Anytime we see area under the graph, we want to think of the definite integral. In this case, we're going from -1 to 1, and our integrand will be the function e to the x. Always write dx when you write an integral. We take the antiderivative of e to the x, which of course is simply e to the x. Use our brackets to show that we still have to evaluate at those limits. We don't need the plus c because it will become 0. We start by plugging in the upper limit first, so e to the 1 minus e to the -1. That's a fine answer, but we can simplify to see e minus 1 over e. Number 2, a metal wire of length 8 centimeters is heated at one end. The table gives selected values of the temperature T of x in degrees Celsius of the wire x centimeters from the heated end. Part A, find the integral from 0 to 8 of t prime of x dx and indicate units of measure. Anytime we are taking the integral of a derivative or a rate of change, because the integral is the antiderivative and this is a derivative, those cancel each other out and we are left with t of x. The derivative goes away. We are evaluating t of x from 0 to 8. So that means we are evaluating t at 8 and subtracting t at 0. Using our table, t at 8 is 55 and t at 0 is 100. 55 minus 100 equals -45, and we indicate units of measure, which is degrees Celsius. Part B, interpret the integral from 0 to 8 of t prime of x dx in the context of the problem. That means we want to talk about what this means in terms of this story up here. So this is talking about how t of x represents the temperature in degrees Celsius of the wire x centimeters from the heated end. So this -45 degrees Celsius represents the temperature change over that 8 centimeters of length. We could say this a couple different ways. We could say the temperature change over the 8 centimeter length of wire was negative 45 degrees Celsius. We've noted what the x represents, or that interval, is the length of the wire, and we've noted what the integral is, that change in temperature. Now, because the change is negative, another way that we could say this is that the temperature decreased by 45 degrees Celsius. So we can say the temperature decreased by 45 degrees Celsius over the 8 centimeter length of wire. Number 3, the population of the United States is growing at a rate of P prime of T equals 2.867 times 1.009 to the T million people per year. Notice this is a rate, and notice how our units are something per something, where T is the number of years since 2015. Part A, find the integral from 0 to 5 of P prime of T dt. So they gave us a function for P prime of T. So I'm going to rewrite this, the integral from 0 to 5. Instead of P prime of T, I'm going to plug in 2.867 times 1.009 to the T dt. I can evaluate this by taking the antiderivative of this integrand. 2.867 is simply a constant multiple, so it can hang out and multiply by my antiderivative. This exponential function has an antiderivative of 1.009 to the t divided by the natural log of the base, 1.009. We put our brackets to show that we're still evaluating from 0 to 5. 2.867, and then I plug in the upper limit first, 1.009 to the 5 over natural log of 1.009 minus 1.009 to the 0 over natural log of 1.009, and we can simplify this, and the value is 14.661. Now, it is also an important skill that we know how to evaluate definite integrals on the graphing calculator. So let's talk about how to do that at this time. I can, when I go to my graphing calculator, find the definite integral command in the Math menu. See Math and then number 9, Function Integrate. But first, because I often need to also use the graph, I like to plug in my function into y equals. So notice I've plugged in my function, the integrand, into y sub 1. I'm going to quit out of this screen, and then I'm going to go to the Math menu and find the integrate command, choice 9. It shows up with that skeleton of the definite integral. I type in my lower limit 0 up to the upper limit 5, and then instead of retyping my function, I recall the y equals by going alpha y equals, and I go to the right to where it says y var, and I plugged it into y sub 1, so I choose that one, enter. Now I go over to where it says d, and I type x for dx. That's an easy way to get it in there since I've already typed it into the y equals, and I don't have to worry about all sorts of parentheses in this area. Press enter, and it'll calculate my definite integral, 14.661, and we verify that that is in fact what we evaluated by hand. Part B, interpret the integral from 0 to 5 of p prime of t dt in the context of the problem. So they talked about p prime of t being the rate of the population growth in the United States. So if it's a rate and we've taken the integral of the rate, the integral cancels out the rate because the rate is a derivative and the integral is an antiderivative. So we take away the word rate, which means we take away the units per year, and we just end up with the change in millions of people. So we can interpret the meaning of this is how the United States population is changing, or because this is kind of future years. It is 2020 now, but this information is basically the projected growth. So the US population, we can say, is increasing by or is projected to increase by 14.661 million people from, and now we look at our intervals 0 to 5. This is the year since 2015, so 5 years past 2015 is 2020. So from 2015 to 2020. Part C. If the population of the US was 320 million people in 2015, what is the projected population in 2020? Well, this is the change in how many people there were from the year 2015. So our P of 5 is P of 0, the population at time 0, plus the amount that it changed over the intervals 0 to 5, which is what we calculated, that definite integral of P prime of t dt. So that is 320 million in 2015 plus the amount it changed by, 14.661 million, which is a total of 334.661 million people. Number 4, for the graph of f of t equals sine of t on the interval 0 to 2 pi. Part A, find the accumulation function capital F associated with f over the given interval. So capital F of x, our accumulation function, is represented by the definite integral from 0, the beginning of our interval, to some point along that interval, x, of the function sine of t dt. We can take the antiderivative of sine of t, which is negative cosine of t, and using our brackets, we put our limits 0 to x. Plug in the upper limit first, negative cosine of x, and then the lower limit plugging in 0 minus negative cosine of 0 makes plus 1. Part B, find capital F of pi over 2, of pi, of 3 pi over 2, and of 2 pi. So we take what we got as our accumulation function and plug in each of those values. Capital F of pi over 2 means negative cosine of pi over 2 plus 1. That's 0, and 0 plus 1 is 1. And then f of pi, negative cosine of pi plus 1. That's negative 1, and the negative of negative 1 is positive 1, and 1 plus 1 is 2. And then f of 3 pi over 2, plugging in the 3 pi over 2 gives us 0 plus 1, so that one's 1. And then capital F of 2 pi, negative cosine of 2 pi is negative 1, and negative 1 plus 1 is 0. Well, what does all this mean? That's what we want to do in Part C, interpret these results found in Part B. Let's take a look at the sine function for a moment. I'm going to sketch a quick graph of y equals sine x over the interval 0 to 2 pi. Notice at first above the x-axis and then below the x-axis. Well, the accumulation function is the definite integral of that sine function, which remember means the net area. So notice that at first, the area is increasing. Now, there's still more area, but then it's below the x-axis, so the definite integral will be decreasing. So notice that, of course, at 0, the integral from 0 to 0 will be 0. So starting from 0, it goes up to 1, and then as we get higher, it's gone up to 2, and that's the highest that it gets. So the accumulation function is increasing from starting 0 up to 1 and then up to 2. So from 0 to 1 to 2, as x increases, from 0 to pi, because of course this is where pi is, at the center of that, in the middle between 0 and 2 pi. Then, because now we start to subtract this area that's below the x-axis, then it decreases. So it was going up to 2, and now it's coming back down to 1, and then all the way down to 0. Why does it end up at 0? Because there's the exact amount of area above and below the x-axis. So those two areas cancel each other out, and we end up with a net area of 0. So to continue our description, then that accumulation function decreases from 2 to 1 to 0 as x goes from pi to 2 pi. We can also say the net accumulation over that interval 0 to 2 pi equals 0. Thanks for watching.